This video is going to be on a little bit of index law review and then exponential functions. So here we have all the index laws, and you should have seen them before in grade 10, but if not, make sure you get them down and you understand how they are working, because it is expected that you will know these rules. So I just got one example just to show something else that works with index laws that is a skill that going into exponential and logs does get used, and it does get tested in IB exams. So first example, so part A, 2 to the power of x equals 16. So you can generally work this out in your head, but it's not always possible in an exam. So the best way to approach this is to make it have the same base. So convert 16 to a base 2, which would be 2 to the power of 4. Once we have the same bases, we can then just look at the powers, so x must equal 4. B approached the same way. This time it's a little bit different. So we've got 3 to the power of x plus 1 equals 9 to the power of x. We want the same base, so we want to write 9 to the power of x with a base of 3. 9 we can write as 3 squared. And then we still have the power of x. We then will need to expand that, so 3 to the power of 2x. Now we have the same base, we can equate the powers. So it'll be x plus 1 equals 2x. So x equals 1. Now let's look at exponential functions. An exponential function is a function of the form f of x equals a to the power of x. A is known as the base, and then x is the power or exponent. With this, a has to be greater than 0, and a can also not equal 1. An important mathematical constant is called Euler's constant, which is represented by the letter E. So you may have seen that before in other things, the letter E within maths. It's called Euler's constant. It's approximately 2.718. And in an exponential functions, E is known as the natural base. There's just some information here on exponential functions when we're drawing graphs. So they've got a general form of an exponential function here. And A controls how steeply the graph increases or decreases. H is a horizontal translation. K the vertical translation. And the equation of the horizontal asymptote is when y equals k. These parts here of where P and A are tell us what the graph looks like. And once again, that's something you need to learn. Example 1, consider the function y equals 2 to the power of x plus 3. First of all, we want to find the y-intercept and the equation of the asymptote. So the y-intercept obviously is just when x equals 0. So y equals 2 to the power of 0 plus 3. Remember, 2 to the power of 0 is 1. So it'll be 1 plus 3. So the y-intercept is at 4. Equation of the asymptote. So remember up here we said the equation of the asymptote is when y equals k, which is the number added or subtracted to the function. In this case, that is 3. So our asymptote will just be at y equals 3. State the domain and range of the function. So the domain is all possible x values. With an exponential, you can put any value into there for x. There's no restrictions on that. So x is an element of R, or between negative infinity and infinity, however you like to write it. And the range is all possible y values. Now, because our asymptote is at when y equals 3, all our values will be above that. So our range would be when y is greater than 3. C, sketch the graph of the function. So I'm just going to draw a really dodgy sketch here. Now we know our y-intercept's at 4. And then we also know that our asymptote is when y equals 3. And we're going to draw that with a dotted line. Now we just have to work out what our graph is going to look like. So we can go back up to here. We know that, and in this equation, if we look at our P and A values, P has to be positive because 2 to the power of x is positive. A is 2, which is greater than 0. So we are looking at this first graph here. And then we just draw it. So we've got the asymptote, and then it goes through the intercept and carries on going. And that's the basic sketch of the function. Part D, using your GDC, solve the equation. So you've got two options with this. You could put the equation in like that and end solve it, or you can graph both sides of the equation, so graph 2x plus 3, and then graph 2 plus 3 negative x, and find the intersection. Or as I said, with something like this, you can end solve it. And if you do that, you'll find that x equals negative 0.490. Example 2. The value of a boat y in thousands of UK pounds is modelled by the function y equals 20 multiplied by 0.85 to the power of x, where x is the number of years since the boat was manufactured. Find the value of the boat when it was brand new. So when something's brand new, it means our time would be 0. It's at the start when we've just bought it, no time has passed. So y equals 20 multiplied by 0.85 to the power of 0, which would just be 20 times 1, so y would equal 20. Now it says find the value of the boat. We know our y is in thousands, therefore it would actually be £20,000. B. Estimate the value of the boat when it is 3 years old. So now times just 3. So y equals 20 multiplied by 0.85 to the power of 3. Put that in your calculator and you will find that the answer is 12.2825. So our final answer in pounds would be £12,283, the nearest pound, because that's what the question does ask for that. And then part C, use your GDC to estimate the value of the boat, to estimate when the value of the boat will be worth half of its original value, which means we are wanting when y equals 10, because that's half the original value. So we'd have 10 equals 20 multiplied by 0.85 to the power of x. Put it into nsolve or graph it. So you would be graphing 10 and graphing 20 times 0.85 to the power of x. Find the intersection, or as I said, nsolve. And you would find it would be x would equal 4.27 years. And that's the basics of exponential functions.